This is Introductory Nuclear Physics, and today we are going to discuss nuclear models. In our previous discussion, we have gone through the liquid drop model, and today our topics are that we will recap the liquid drop model. We will go through the shell model. We will talk about the predictions of nuclear spin, then predictions of nuclear parity, and finally we will briefly discuss the exchange field particle model. We have already seen that liquid drop model is capable of predictions of binding energies of various nuclei to large accuracy. It can predict emission of alpha particle and beta particle decay in radioactivity. We have now seen that the theory of compound nucleus leads to the nuclear fission process, and understanding of fission process becomes easy. However, this model fails to explain the stability of the nucleus with the special emphasis to such a number, for example, 2, 8, 20, 28, 50, 82, and so on. We don't know how these can be fitted in the liquid drop model. It fails to explain the measured magnetic moments of many nuclei. It fails to explain the spin and parity, which we hope will be explained through the shell model. So we move further and we go to the shell model. Shell model is based on the principle that we will use Pauli exclusion principle for the structure of nucleus. And similar to the electron shells, the nucleus has shells and the nucleons revolve in those shells, or they occupy those shells. The shell model is just like atomic shell model. Filled shells have great stability. There are energy levels that are allowed, and there are regions where there is no allowance for stay. In shell model, each nucleon moves in net attractive potential. That is the average effect of its interactions. The potential has a constant depth inside the nucleus, and outside the nucleus it goes to 0. It also excludes the possibility of nucleon-nucleon collision, so they are not interacting. Hence, the nucleons that constitute the nucleus can move freely inside the ground state nucleus, and they can orbit about the center, and it is the independent particle model idea. Behavior of each nucleon can be understood by solving Schrödinger's wave equation for the potential, and the bases are again that the standing waves are constituted if they are the integral multiple of the wavelengths. So it has the same role in nuclear physics as we see further in Hartree-Fock theory in atomic physics. So shell model has an important role to give in-depth understanding of the nucleus. The similarity between the shell model and the Hartree-Fock theory is shown here. Shell model has nucleons that move in the attractive potential. And we see that the electrons move in an attractive potential according to Hartree-Fock theory. Nucleons obey Pauli exclusion principles. The electrons obey Pauli exclusion principle in Hartree-Fock theory. The nuclear potential VR depends on the n quantum number and the L quantum number. The atomic potential depends on n and L in a similar fashion. The atomic spin, orbit, coupling, or interaction is present. Similarly, the nuclear spin, orbital, coupling, and interaction is present and is responsible for explaining the angular momentum. The difference between the shell model and the Hartree-Fock theory are following. Potential VR is a square well with a rounded edges in the shell model for the nucleus. The N, the radial node quantum number, or the principal quantum number is N radial plus L, and there is no upper limit for L. The strong inverted spin orbital interaction is there. S and L coupling is there. The SL nuclear coupling is about 20 times stronger as compared to the atomic spin orbital coupling. The spin orbital interaction is not magnetic in origin. For the shell model, these are the things. And if we look at the Hartree-Fock, the potential is spherically symmetric. It is not square. The principal quantum number is N. There is upper limit on L. And the spin orbital interaction is L dot S. The spin orbital interaction is a magnetic in origin, and it is not independent of the magnetic effects. So these are the major differences that we have to keep in mind in the shell model. And as we progress and make the shell model available, we see that shell is basically based on the energy levels diagram, similar to the atomic and molecular shells. Here we can see the part without L dot S coupling. If it is the case, then 1S, 1P, 1D, 2S are the lines. However, if there is a spin orbital coupling within the nucleus, then for each case we see and register there is splitting. 1S has the same, however 1P has 2 possible, 1D has 2, 1F has 2, and so on. Now let's see how the things are getting occupied. For P orbital, the L value is equal to 1. L value for S is equal to 0. When S is equal to 0, the 1S state has only half because of the S value. S is equal to half. S can be plus minus half. So S has 2 possibilities. Therefore, the 2 electrons will occupy this kind of a state for the atoms. However, for the nucleons, the 2 nucleons will occupy this state. Now, let us check it for L is equal to 1. L is equal to 1, S can be plus minus half. Then L plus S is 3 by 2. L minus S is half. So we can see 1P has 2 possibilities, 1P 3 by 2, 1P 3 half. And for P equal to 3 by 2, the total number of the nucleons that will occupy is given by 2 multiplied by 3 by 2 plus 1, which is equal to 4. 2 multiplied by half plus 1 is 2. Similarly, 1d 5 by 2 means the 5 by 2 multiplied by 2 plus 1 is equal to 6. This 2 as half is with the 2. 1d 3 half is actually 4. So now let us do the summation. For the first, we have only 2 nucleons. For the next, we have 2 plus 4, 6, plus the 2. So up to this state, 8, completely filled 8. And then if we move further, we see 6 and 4 and 2. So all to all, 8 plus 6 plus 2 plus 4 is 20. 20 plus 8 is 28. 28 plus all this together is 22. 28 plus 22 is 50. Now you can see these are the numbers 2, 8, 20, 28, 50 that are the magic numbers that were not really available with the help of a compound nucleus or a nucleus that is looking like a liquid drop. So shell model is able to interpret very nicely the magic numbers. Prediction of nuclear spin. Both the neutrons and the protons have to be filled independently. If you fill all the neutrons and the protons according to 2j plus 1 values in various orbits, then of course you are going to obey the Pauli exclusion principle. Once all the nucleons are used, then you go to the top level, the last occupied state, and look how they are arranged. If there is any unpaired nucleon there, then the spin of the nucleus will be the value of the angular momentum of that state. And that's how the nuclear spin will come into existence. Now, if it is the case of one proton and one neutron which is remaining unpaired, then spin of the nucleus will be the algebraic sum of the angular momenta of these two states, taking spin up as positive value and spin down as negative value. And we will make sure that we will fill up spin first. So the shell model with this idea fills the shells obeying Pauli exclusion principle for the protons, Pauli exclusion principle for the neutrons, and we get shell filled and we get the nuclear spin. Now, if we want to see how the shell model behaves according to the nuclear parity, mathematically speaking, parity is actually the behavior of the wave function under the reflection of space coordinates through the origin, which determines the parity of the system. So under the reflection of the space coordinate, that x goes to minus x, y goes to minus y, z goes to minus z, the wave function can change sign or can remain the same. So in the case the wave function does not change any sign upon reflection, the space of the coordinates, the parity is even parity. And if it changes the sign, the parity is odd. So parity can be computed for a nucleus with the help of this relationship with -1 to the power of a sum of L protons and L quantum number for neutrons. So all together will dictate the parity, where the total value of L for protons and the neutron is summed as a power of -1. So it can be even or it can be odd. And on the basis of this, the reflection, under the reflection, a nucleus will show its signature that it is the left hand becomes the right hand, or the right hand becomes the left hand, or it remains the same. And that is the parity. Let's talk very briefly about the Yukawa's exchange field particle model. According to Yukawa's theory, every nucleon continuously emits and absorbs pions. If another nucleon is nearby, then emitted pion will shift across to it instead of returning to the parent nucleon. So the associated transfer of momentum is equivalent to the action of force. And this is the first time that force was redefined as an action, and action due to some exchange of particles. So there is a field in which particles are being exchanged, and the exchanging particle exerts momentum, and therefore it exerts force. The nuclear force are repulsive at very short range as well as attractive at the nucleon distances, and it was due to the exchange of pions. This mystery particle was not really available until 1947, when British physicist Paul discovered the pion, which has the property that Yukawa predicted, but they decay rapidly into the long-lived muons. Yukawa received a Nobel Prize in 1949 on this experimental discovery, that his theory is really very, very important. So the nuclear model is now telling us another complicated and a new thing. And it is telling us that in a region where the quarks are of the radius of 0.3 femtometer, the pions exchange makes it repulsive, and it makes them within the radius of the nucleus the attractor, and the mass of the exchanged particles is a measurable thing, and it is possibly, it can be made available in nature and can be detected. In 1932, Heisenberg had suggested that a neutron might emit an electron to become proton, and a proton on absorption of an electron can become neutron. In 1935, Yukawa proposed mesons. He said the mesons are involved in the nuclear forces. So he said that all the nucleons have a cloud of one or more mesons. Thus, nuclear force is basically between neutrons and protons, or between neutrons and neutrons, and protons and protons. It is due to the exchange of charge mesons or neutral particles. And so there are currents of pi plus or pi minus, and the neutron can get converted into a proton through this interaction, that a neutron actually is can become a proton and can allow a pion minus to go out. Then proton will absorb it and will become a neutron. So in a reverse process, if the neutron is going to absorb a pi plus, it is going to produce a proton. So a proton is can decay into a neutron and a pi plus. This kind of exchange and the equations and the proposal became really a matter of fact when it the mesons were discovered and their properties were detected, then Yukawa's theory was taken very seriously. We can calculate the exchange particle masses using uncertainty principle. Here we see that a repulsive force due to the particle exchange can be like this, that the balls are being thrown or repelled. And the attractive forces due to particle exchange can be where they are being exchanged and the attractive force is present. Now, if you want to find out the nuclear force, it has a maximum range of 1.7 femtometer. Suppose a meson travels with the speed of light, then the energy is mc square, and the time taken is r divided by c. R is the radius of the nucleus. Substituting then this meson mass can be detected and measured, and it is about 2 into 10 to the power minus 28 kg. It comes to be, and in terms of the comparison, we can say that it is about 220 times the mass of the electron, the rest mass of the electron. So after the Yukawa's idea, the actual charged pions were detected with a mass of 273 times the electron mass, and they were the massive electrons, and they were discovered. So Yukawa's idea was correct. The exchange of particles is taking place with the nuclear force. So nucleus has a complicated model of exchanging particles with each other. As a matter of fact, all the forces are doing this. So a new name for forces came into existence, the interaction. All forces are basically interactions, and they are exchanging particles with each other, and therefore the force exists. In some cases, the particles are very, very massive, therefore the range is very short. When they are really massive particles, the ranges become very short. And when the particles have almost zero mass, then the range becomes infinite and very large. For the case of electromagnetic interactions, the exchange particles are the photons. And the photons have almost zero mass, and therefore, for the zero rest mass, their ranges are infinite, almost infinite. So the electromagnetic interactions are taking place at very large distances. However, for the weak interaction and for the strong nuclear interaction, the exchange particles are massive. And once they are more than the mass of the electron, then they cannot travel far away. And this particular mass is 220 times the rest mass of the electron. It is much heavier as compared to the electron. Therefore, the short range of the strong force is observed. So we can safely say the ranges of the forces or the interactions are actually inversely related to the masses. Masses of the mediating particles or the particles that are exchange particles. Yukawa changed ideas. Yukawa gave the concept of new way of thinking about the force. And that's how now we know very well that Abdus Salam and Gelashov and Sheldon's theory on weak interaction is also a type of interaction in which mediating W particles and Z particles are exchanging the weak interactions. Here we stop, and we will move further about the nucleus and the decays and the nuclear forces and their effects and the stability and instability of the nucleus in coming lectures. Thank you so much.